Okay. Yeah, technically it's recording now. Well, this angle, I don't know if this angle is good, but well, anyway, it's an angle. They are recording there also, the other angle. So two angles, two complementing cameras and so on. Yes. Really useful. Yeah. So you live here in Shenzhen?
Yeah, in Shenzhen.
Okay. How long have you been here?
In China.
China. Many years already.
40 years.
40.
Wow.
Wow. Amazing.
I live in Beijing.
How about you?
2 years.
I lived in Beijing like 6 months or so, 2015. I was posted there. Yeah, the microphone, right? I have to put it.
Beijing is nice sometimes. Wait,
Hello，大家好啊！虽然可能还有一些朋友还没有到，没关系，我们也可以先随便唠一会儿。然后，我是露露，是 Homebase Lab 的主理人，然后另一位 Zoe 还有 Jerry，然后思睿都是我们 Homebase 的小伙伴。然后大家今天晚上有任何的问题都可以随时找我们。然后今天其实我是看到了很多我们的老朋友来的。当然也有新朋友啊，给新朋友再介绍一下碰杯。我们其实是在每周五、周六晚上都会做这样的学术酒谈活动。那过往的话，除了我们今天这场的量子呀，然后包括以前我们还做过一些哲学、物理，还有一些复杂性的科学。所以大家要是感兴趣的话，都可以关注我们后续的活动，包括我们下周。五周六的话，有一场是关于 AI 的，然后还有一场是关于欧洲的建筑美学，因为也希望能够给大家带来更多元化一些的，就是除了一些比较深奥的理性学科之外，我们也可以欣赏一下也比较轻松的一些艺术史。对，然后大家感兴趣的话都可以关注，然后另外可以扫码进今天的社群，左边的是我们今天晚上的小群，我们今天的一些课件包括会分享到群里。还有今天，因为我们特别有一位很厉害的摄影师 photographers，so 我们最后也可以在社群里分享今天他拍的照片给大家。然后后面的这个群的话是我们平时活动的群，所以大家也可以在里面关注到。今天的话也是活动会1个小时的交流啊的1个小时的我们的一个分享。那大家可以看到，对于老朋友来讲的话，可以看到我们今天多了一个大屏幕，就是我们特别，我们碰杯60多期做到现在，终于有赞助商出现了，就是我们去，因为今天毕竟是一场全英的分享嘛，然后之前艾文来过一次的时候，也会担心大家觉得会不会说，我们全英的分享量子有一点门槛，所以这次我们去找到了这一家叫英诺，它叫来化科技。然后他们专门做一些 AI 翻译的。然后除了我们今天会用到的这个会议系统之外，然后它还会完了，这段不能让他们看到，还没录呢。对，就是它有一个这样的小的翻译器，然后就这样磁吸到手机上，然后平时就可以使用了。我觉得还挺方便的。然后我这就不打太多的广告了，那边会有我们的那个它产品介绍，还有翻译器，如果大家感兴趣，就如果有场合需要用到的话，就还是挺方便的。然后今天我们也有这样的功能可以给大家就是看一下它是怎么使用的。一般这种他们的会议系统都是那种1000人大型的论坛会议才会用的，也是非常感谢他们看得起我们这种小活动，愿意给我们来赞助使用。对，然后就我话不多说，然后thank you Ivan and come to come there again to sharing the black hole. So let's welcome Ivan. No.
No. How do you change the slides? Okay. Okay. Thank you very much. Yeah, it's here. Okay, you will have the translation here. This side, somewhere. Somewhere. Visual, My Chinese is Mamahu. So I will speak in English, but you have the translation there. My name is Ivan Arraut. Is the right pronunciation. I work here in Macau, and before I was in Hong Kong. My PhD is from the University of Osaka in Japan. What else? I was the SPS fellow in Tokyo, and I was CIS fellow in Beijing. Master and bachelor were in Colombia. So, of course, my expertise is gravity cosmology and quantum field theory, and I want to talk about the concept of information in black holes. And at the end, I will mention a little bit of quantum computers, because anyway, information is a very general concept. And you can basically, the black holes contain information, and you can store information in bits, but at the quantum level, we use qubits. Yeah? So I will explain why it's a qubit, what is a bit, and so on. Later. So here's, of course, for going slowly, we have to understand that there's a theory called quantum mechanics, which it reflects how the universe works. When we unify with special relativity, we become quantum field theory. But this theory started in 1900 and 1905. The early stage when Max Planck and subsequent Einstein postulated that the radiation and as a consequence of light, all the electromagnetic radiation come in small packages. It was the only way to match this curve, which is the black body spectrum of radiation of the black body. So this is about the story, and then Einstein came with the photoelectric effect. He took the idea of Max Planck that the electromagnetic spectrum came in small packages, and then he postulated that the light come in small packages called photons. That's why it's called quantum. Quantum mechanics, quantum comes from a small quantum. So the most fundamental package, which is the photon. So the photons collide a material and eject electrons. This is the photocell. This is the principle of photocell. It's one of the oldest quantum technologies already available. Then, of course, quantum mechanics evolved, and it became more serious when Heisenberg, Schrödinger, and others developed it more formally, and it became famous. This is the famous paradox of the cat, whether the cat is alive or not, because in quantum mechanics, we work with superposition of states, quantum states. For example, if we put a cat in a box, the cat is alive on that at the same time, assuming that something can kill it inside. And we have to assume, if we don't know what is the final output, we have to assume that both are possible with different amounts of probabilities, not necessarily 50-50, but the key point is that these two events interfere with each other. They mix each other. And this will bring out the concept of qubit later. Because in computers, if you know a little bit about computers, when you type a word or you type anything, the computers process this information in terms of zeros and one. 0, 0, 0, 1, 0, 0, 1. But they don't mix the zeros and 1. So the idea of qubit is that you can have a 0 here and a 1 in a single object, and they mix somehow. So this is the concept of qubit. Basically. So quantum mechanics work with superposition of quantum states. If I put a particle here in this room and I cannot see it, I have to assume that the particle is everywhere. Okay. So this brought out the Heisenberg uncertainty principle. Basically, if a particle is moving somewhere and I don't see the particle will have a well-defined momentum. But I will not know the position. I have to assume that it's everywhere inside the room, consistent with the constraints of the room. But if I try to observe a particle, for observing a particle, I have to hit the particle with a photon. example, I want to observe you, I need to hit you with light. The light has to collide you and the light come back to me, right? What I see is the reflection of light coming from you. Right? I don't see you, I see the reflection of light. Then the same is when you want to see a particle, an electron, you have to collide with light. But when you collide with light, you destroy the pattern of evolution of the particle, and the particle start to lose its dynamics, its natural dynamics, so you destroy its momentum. That's the uncertainty principle, and it's one of the most fundamental ideas in mechanics. And this is the famous double slit experiment. If you draw electrons or photons or particles, the particles have associated a wavelength to them, and if that wavelength is longer than the separation of the screens, it means that the particle cross both slits simultaneously. So the particle, imagine a person is something blow in mind, because it's like that door is open, this door is open, it's like me, I'm going out from this room, and you will ask which door I want to. Then he went out from both doors at the same time. That would be crazy. No? It doesn't happen at our scale, but at microscopic scale, it's happening. Because the smaller the particles are, the longer the wavelength. What happens is that we humans, we have a very short wavelength. We have a wavelength, we can behave as a wave. But there are two things, is that we interact with things, we touch things, we are touching tables, we are touching the floor, we are touching everything. So obviously, we are interacting. When we interact, our wave function collapses. Yeah, this is the Copenhagen interpretation. Well, at the same time, we are too big, too macroscopic. Our mass is too large, our momentum is too large. And even if I try to stay still, my heart, my breathing, the fluids of my body, the blood, etc., has a huge momentum compared to the quantum scale. So my wavelength will be very short. So I will behave as a particle. So I will go out for this door or this door. When you go to the electrons and photons, the wavelength becomes longer, they behave more like waves. So they will be able, even if you throw one by one, they will be able to cross both. And how do we know that? Because the experiments are telling us that. It sounds like cheating, but no, it's not cheating, because when you do the experiment, this is what the experiment is telling you. You throw electron by electron and the one by one. And what you see is that the impacts on the screen are consistent with the interference, constructive and destructive. When there is destructive interference, the electron doesn't collide. When it's constructive interference, the electron collides. Right? It's like if you were a person, and if you were quantum, imagine that you were quantum, you became quantum. You could be in this room everywhere. As long as you don't interact with anything, you could be everywhere. And somebody asks, where is, well, I wouldn't say name, myself, Ivan. If you don't know where is Ivan, you can say, it's inside the room, but I don't know where. So I have to construct a wave function, and I have to zoom all the possibilities. I have to zoom here, over the whole volume of the room. And this is my wave function. And that wave function gives me the probability for me to appear somewhere in the room. Yeah. And of course, the uncertainty principle is a special case of the most general principle called complementarity, is that we have a set of complementary variables. So in quantum mechanics, we cannot define all the variables of a system. We can define either one or the other. We can define position or momentum, not both. We can define angular momentum or angle. We cannot define both. And so, I mean, there is a set of complementary variables. Then, when I want to define the dynamics of a system, I have to select which variables I want to fix, which variables I want to keep uncertain. Or I can keep partially inserting both. And both of them are connected via Fourier transformation. Mathematically speaking, it's a Fourier transformation. And when we are working a problem in quantum mechanics, we have to select either position space or momentum space. Position, the operators behave different in position or momentum space. If you select momentum space, the momentum operator behaves in one way. But if you select momentum space, it's different. They are both connected via Fourier transformation, and both spaces contain the same information. And this is what I was talking about. If we put a particle inside a box and I close my eyes, well, not close my eyes because if the particle is inside the box, I cannot see it. And somebody asks me, where is this particle? I will say it's everywhere consistent with the constraint. So I have to construct a wave function and assume over all the possibilities. This is what Richard Feynman discovered. Richard Feynman, who was a genius, a simplifier, the guy simplified physics. Calculations which Dyson, Schwinger, and the others make very difficult. Feynman simplifies in a few steps. He created Feynman diagrams. He even say, when I assume all the possibilities for an electron to be somewhere, I can recreate the wave function. He was a guy very intuitive. I think one of the last great characters, probably one of the latest great characters the physics had. Maybe there will come more, hopefully. Let's see. So now let's talk about black holes, because I did this introduction is because I will analyze the quantum effects in black holes. Therefore, looking quantum effects in black holes, we need to know what is quantum mechanics first. Well, black holes, if I ask you what is a black hole, what did you hear in the media, or who can tell me what is a black hole? Is somebody want to say something, or well, shy audience? Okay, I will say myself. It's a huge concentration of mass. Technically, any object, if I make it compact enough, can become a black hole. For example, I can take over a planet, the Earth, and I can shrink it to 3 or 4 millimeters, all the mass in a small region. It's a huge density. Density is huge, and that's a black hole. A very small black hole is a black hole. But of course, the black holes don't form like that naturally. Naturally, they come from collapse of the stars. Then what happens when the star dies? Then start to become compact until it crosses a region which is called gravitational radius, which becomes the event horizon, and then all that matter becomes trapped. Then what happens? The black hole has a region called event horizon. Why is it called event horizon? Because once you cross it, you cannot escape. You cannot escape, no matter what you do. You can invest all the energy you want, infinite amount of energy. There is no way you can escape, because the space-time is telling you that the only direction that the geometry is allowing you to take is the singularity of the black hole, the center of the black hole. Then you will finish dying, of course. Maybe you will die before when you cross the horizon, because gravity is huge. It's huge there. And there are many interesting effects. There's time dilation, gravitational time dilation, there's dragging effects. The black hole rotate also. They are not spherical, they are more cylindrical geometry because they rotate. And we know they exist because it's not fiction. It's that we have taken a photo, a picture. Then how can they take a picture of the black hole if you cannot see it? Because what happens is first, how could they detect a black hole? What the gravitational effect it creates. Even if you don't see something, you see that there is a disturbance in the motion of objects around. Then you say there must be an object here affecting the motion of this guy. Then after the investigation, it's consistent with the black hole. Then after, how can you see the black hole? Why it creates hollow? Because when the light comes from the back, it curves and comes outside. That light is outside the event horizon, so it can escape. It's not inside the event horizon. And the light will enter the event horizon, cannot escape. Not even the light can escape a black hole, because gravity is too intense. So there is always any planet, in our planet, and in Jupiter, and anywhere, there is an escape velocity. For example, when we throw a rocket or a satellite, there is a minimal velocity required for you to put in orbit an object. So let's put the famous Newton experiment. He imagined that there was a cannon in a mountain. The cannon started to shoot, and then the bullet started to fall, parabolic motion. But if you shoot it very fast, there is a moment where the object rotates like the moon. That's why we say the moon is on free fall. It's free fall is because gravity is falling, but the centrifugal effect compensates the falling. The centrifugal effect, when you rotate around an object, you have an acceleration which causes you to go out. Then, gravity compensates that, then you are in free fall. In the case of black holes, there is no escape velocity. You can do whatever. It's infinite. I mean, you can try to escape and there is no way. But that's classically speaking, not quantum mechanics. In quantum mechanics, anything is possible. In quantum mechanics, a particle, for example, I cannot cross this crystal. If I try, I will collide. But in quantum mechanics, a particle can penetrate this barrier. That's called tunneling effect. Tunneling effect, which allows the process of fusion in the sun. That's why we have the sunlight, for example. It's a huge amount of energy. Then let's continue. This is the first, well, don't get scared about the mathematics. I think some of you are familiar, some of you know. I will not talk so much about the math, but this is the spatial solution. We call it because it's a guy called Karl Speicher. I think it's German. He discovered the first solution of black hole. Because Einstein, when he discovered his theory of general relativity, which is the theory of gravity, which is superior to the Newtonian gravity, and it's superior because it predicts more things than Newtonian gravity. Well, for example, gravitational waves, time dilation, dragging effect, all these things Newton cannot predict, expansion of the universe, Newton cannot predict, many things Newton cannot. So Einstein theory is superior. But what happened is that Einstein believed that his equations couldn't be solved. Well, came this guy, Speicher, and he solved it. He could solve because he took advantage of the spherical symmetry, of course, which simplified it. And this is the famous spatial metric. You can see Newtonian constant, mass, R. This is familiar for you, no? It's like Newtonian solution. This is Karl Speicher, this guy, with a huge mustache here. Maybe was it fashioned by the time, I don't know. The issue is that this is the metric, the same metric you saw before, written in different ways, this one. Time component, spatial component, angular component. Take into account that in general relativity, as well as in special relativity, we don't work in three-dimensional space, we work in four-dimensional space. Because the time is the fourth dimension. So in reality, we have a tetradimensional space-time. And in the same way as we define vectors in 3 dimensions in Euclidean geometry, we can define 4 vectors in relativity, which is the right way to define it. This is important because this is how we define invariance, this is how we define in flat space-time that is speed of light invariant, it's a change. In curved space-time, more interesting things happen, of course. The point is that this solution is telling you that when you cross this is the event horizon, a spherical solution. If you go below this radius, you cannot escape the black hole. If you are a distance larger than this radius, you can escape. This is why it's there. And there is another phenomenon, of course, time dilation. If you saw the movie Interstellar, I think you watched the movie Interstellar. You watch it? I watched it also, nice. Everything is real except the end. The end, they took some fiction, they did something strange. But the movie accurately said that the time flows in different rates in different points of the universe. Remember, when they were in the Miller planet, there was a planet rotating around black hole. Since the gravitational field is so intense, the time flows different than over time. So 1 hour there was 7 years from here. Actually, when you approach to a black hole, the time stops near the event horizon. And then if you check your clock there, you see the time flowing normal. If we check our clock here, also normal. But when we compare the clocks, for us, maybe it's millions of years, and for this guy, it's only 1 hour or so, depending how close is the person to the event horizon. That's called gravitational time dilation. It's an effect proven experimentally. It's not fiction. It's not It's not like Marvel movie. It's really, really a serious effect and it happens. Well, I think I will mention it later. I think I advanced too much, but the time moves near the black hole is slowed down. I will put a more basic example. If we compare the time of the year and the time of Mars, for example, what will happen? Of course, almost the same, almost, but not exactly the same. Because Mars is smaller, Mars has less gravity than the Earth. So technically, the time in the Earth slows down with respect to the time of Mars. So if we put a clock on Mars and a clock on the Earth, initially we will not notice any difference, but after 10 years or after a few years, we will notice some difference. And it has to be corrected. And this effect is general. So it means you will age different here than in Mars, assuming that you can live in Mars. Or you will age different here than in a black hole. Because the way of the time flow is different. Still, we are not talking about information. Well, it's interesting that I wanted to mention. Another effect is GPS. You know what is the GPS, no? So the GPS, you have to put some satellites sending signals to your phone and you're using map very nice accurately. But the accuracy of the map depends on the accuracy of the time of the signals. And because the satellites have less gravity than here, because they are far away from the Earth, the time flows different to us. So over time slows down with respect to the satellite gravitational. And we have to correct it. That's corrected manually. We do it. And also the satellites move very fast because they have to keep in orbit. There is a relativistic time dilation, which is come from special relativity. When you move faster, when objects move faster, of course, we perceive over time dilates with respect to the other. So those two effects tend to cancel, but they don't cancel exactly. But we have to correct it manually. If we don't do that correction, your GPS will not work well. So this proves that relativity is true. It's a serious theory. It's not fiction. And that the time is not absolute. Technically, we can travel to the future, but if you near to the speed of light, or if you're approaching a black hole, but you cannot move to the past. Something which like relativity doesn't allow us to go to the past. So now, Hawking, in a seminal paper, Stephen Hawking, you know Hawking, no? Stephen Hawking, he was in a wheelchair almost most of his life for a disease. And he passed away a few years ago. His supervisor was Roger Penrose, who got Nobel Prize a few years ago, I think, right, for the discoveries in black holes. And because they detected black holes and these things, and then nice. But Stephen Hawking did a nice discovery. I don't know if it's inspiring condensed matter systems or not, because it happened also in fluids. For example, when you put a fluid, you open this liquid, there are drops escaping. The liquid is escaping, and also there is if you decrease the pressure, the liquid starts to escape. If you increase the pressure, of course, the liquid tends to stay there. If you decrease the temperature, technically nothing will escape. If you go near to the zero absolute from a liquid, but there is a phenomenon called quantum deflection, which allow particles to escape even if classically they are not allowed. The same happens in black holes. The black holes are supposed to eat and not emit anything. But if you apply quantum mechanics around issue, and it has to be a semi-classical approach because you don't have a quantum theory of gravity. If we put a quantum field around the black hole, it comes out that particles can escape from the black hole. But of course, you don't want to enter a black hole because the black hole you will escape will not be yourself. It will be a bunch of particles disintegrated. So it's not nice. It's not a nice thing. So the point is that particles can escape from the black hole. That was the seminal discovery of Hawking. This is the expression he found. This is the black body spectrum. The same black body spectrum is reproduced by the black holes. But there is a problem here. and I will explain it later when we go further into the information issue. Why the black holes can evaporate? Well, there's a quantum effect. There's a quantum effect because the picture, naive picture is the following: the vacuum has energy. The vacuum, if I empty this room, if I evacuate everything, and if I release the air, I close it, I take everybody out. Even if I empty this absolutely vacuum, the vacuum has energy. Because the vacuum, quantum field theory is telling us, quantum field theory is the unification of quantum mechanics with the special relativity. Because in physics, we are trying to unify theories. We try to unify. We are trying to find general unified theories, etc. But by these unifications have been step by step. Then when you unify quantum mechanics and special relativity, it becomes quantum field theory. And interpretations are different because in quantum mechanics, we interpret the wave functions and the probability of finding a particle somewhere. But in quantum field theory, we can interpret the solutions as wave functions, well as a quantum field. It's different, it's a different interpretation. It sounds short, but for the moment, believe me that the vacuum has energy. So the vacuum creates pairs, particle and particle. Particle and particle created and disappear. They are created, disappear. If you put an antiparticle near a particle, what happens? They annihilate, boom, and they emit radiation. But the vacuum is permanently creating those pairs and destroying. So technically, if I am able to expand the space like this, so I can extract. I can separate the particle from the antiparticle, right? And that's what the black hole does. Actually, when this process occurs near the event horizon, one of them goes inside and the other escapes, right? And this is called the picture, nice picture of the Hawking radiation. But there is a better explanation. Of course, the calculation of Hawking rigorously is not with this picture. This is the interpretation he gave. And we accept it because we know vacuum energy is true, it's a reality, it exists, and it makes sense, of course. Well, really what Hawking did was to compare two vacuums. The vacuum before the formation of the black hole with the vacuum after the formation of the black hole. Let's assume there is no black hole here. I can define a vacuum, and the vacuum creates the particles. And after the black hole formed, I can define again a vacuum. But then after I have to compare both of them. In this comparison is where there is a discrepancy, and this is where the emission, the thermal emission appears. For understanding a little better this picture, the energy time, there is something called energy time uncertainty principle in quantum mechanics, which allow particles to appear and disappear from the vacuum. The heavier the particle, for example, particles which are very heavy, they live shorter time. When they appear pair, and, for example, proton and antiproton, when they appear from the vacuum, they live less than electron positron. Because electron positron, they have less mass. They can live longer. They can live longer. Because energy times time is some kind of constant. Then the larger the energy, so mass and energy are equivalent in relativity. Then larger mass, less time you can live. Well, it's not related to being big or not. It's related to the world of the particles. No? Then in quantum mechanics, when we analyze the quantum harmonic oscillator, this is the solution of a quantum harmonic oscillator. Who doesn't know the harmonic oscillator? Classical physics. A pendulum. Pendulum is harmonic oscillator. Classical. The string with the block moving, high school. Harmonic oscillator, classical. When you quantize, when you apply quantum mechanics to the harmonic oscillator, you obtain a wave function, a solution, blah, Hamiltonian, etc. And at the end, you obtain these energy levels. When you realize that the lowest energy level of the quantum harmonic oscillator is not zero. It has a finite amount, it's a finite quantity, 1/2 h bar omega. So it means the vacuum has energy. Now, when we go to the quantum field theory, we have to sum all those frequency modes, and it gives you a huge number of those. But anyway, no matter what, that's the vacuum energy. And we know vacuum energy exists, and it has effects. This is another way to see the vacuum energy. The ground state level has, we don't care the quantity, what we care is that it has some value. So in other words, I empty this room, I empty everything, and the vacuum has energy. This has energy. And we have this Casimir effect. We put two parallel plates, one in front of the other. Even if we empty everything in vacuum, they feel some force attracting to each other. And that force is because of the vacuum energy. It has been proven that it's the vacuum energy that produces this effect. That's called Casimir effect. Then it has been proven experimentally that there is vacuum energy. How do we know also that there is vacuum energy? The accelerators. Particle accelerators, when you accelerate two particles and collide them, boom. And suddenly from the vacuum emerge some particles. The Higgs particle itself, for example, the Higgs was discovered in CERN, 2015 probably, or 14, I forgot, 15 or something.
Something.
2012, exactly, thank you. 2000, yeah, I was PhD student, it should be 2012. Then, how do you think those particles emerge? They emerge from the vacuum. Well, why they can emerge? Because you have to inject energy. When you inject energy, bam, you can create new particles. But those particles, they are unstable. They disappear quickly. So what these guys do is to analyze how they emerge and how they decay. Yeah? And how can they appear? Because the vacuum has energy. You are injecting energy to the vacuum, you are extracting that particle from the vacuum. That's what you are doing. That's what the theory says, and the theory matches with the experiment. So vacuum energy allows the black hole operation. Why? Because this process of particle and particle creation, when it occurs near the living horizon, one of the pairs go inside and then the other stay alone, lonely, and it has to escape. Why it has to escape? Conservation of momentum. If something goes, imagine that two particles go like this, emerge, disappear, emerge, disappear, emerge, disappear. But suddenly there is a new horizon here, and this particle was eaten, the black hole. This one, by conservation of momentum, this one has to go the other way. Momentum conservation, basic momentum conservation. Right? You know momentum conservation. No? If you are in a ship and you move in one direction in a boat, what happens with the boat? Move to the other direction to keep the momentum zero, right? If the ship is not moving, momentum conservation, right? So Hawking did actually. Hawking, of course, an authentic genius, of course. What he did, his calculation is quite complex, it's complicated. You need to know Paris diagrams, his supervisor, Royal Paris, which compactify space-time mathematically. You can make a compact map of the space-time. And then you can, what he did was to compare two vacuums. The vacuum before the formation of the black hole and the vacuum after the formation. Before the formation of the black hole, there's no black hole. I define a vacuum here, trivial vacuum. But for defining a trivial vacuum, I have to define a quantum field. I define my quantum field. Quantum field is, well, imagine that there is some particles here. Yeah, whatever. And you can define a vacuum, the void of particles. After the formation of the black hole, I define the same field here. The same field. But it happens that some modes go inside the black hole, some of them remain outside. And then when I compare, I can define my vacuum here. Yeah, I can define a vacuum. But this guy, when he compares his vacuum with this guy, there is a disagreement. Serious disagreement, and one of them perceives particles. Obviously, after the formation of the black hole is where the particles emerge. Yeah. And the calculation is as simple as doing the whole Ball transformation, which is what Hawking did. We just did couple of transformations and you realize that the frequencies, positive and negative mix, pure space-time, it doesn't happen in flat space-time. So, well, recently, some work, doing myself and others, and we realized that the picture of the black hole can be seen as a mechanism of spontaneous material, because in talking about this was to compare to vacuums before the formation and after the formation of the black hole. Then when we have this scenario, we can reproduce a mathematical object called Lagrangian, which defines potential. And this potential defines the equilibrium conditions of the system. What is the equilibrium condition of a system? For example, you are comfortable seated here now. Everybody is sitting comfortable, nice. This is your equilibrium condition now. Nice. Imagine that that's before the formation of the black hole. Now imagine that the black hole gets formed. It's created here in our life. That's equivalent to having an earthquake. The building starts shake the building. So this is not your equilibrium condition anymore. You will be in an unstable equilibrium, and you will be looking for a new equilibrium condition, which is most likely the floor. That's my new equilibrium condition. Yeah? So it's the same. Before the formation, this particle number operator is 0, which is when you apply the derivative with respect to n equals 0 here, we have two solutions, n equals 0 and this one. N equals 0 is before the formation of the black hole, and n different from 0 is after the formation. It happens when this parameter is negative, which is precisely what happens in collective behavior systems like thermomagnetism and others. It's an analogy, of course, but it works. So I will not emphasize so much in this. This is the same picture as before. Particle to particle move, created, they create and destroy, create and destroy. There's no black hole, they remain like this forever. Randomly, particle and particle create and destroy. When there's an event horizon, one of these guys go and you escape. Ignore these equations. I don't want to scare you, but this is related to this solution. Actually found by myself and other guys. So the issue is that the black hole operation can be represented as a mechanism of spontaneous interacting, which is what I was explaining just now, is that you are here right now. If this potential is here, you are sitting here in the center. When there is an earthquake, you are here now. This is unstable. Any perturbation sends you to the floor in any direction, somewhere. We call this a spontaneous interacting. Where does it happen? In superconductors, it happens in ferromagnetism, it happens in many systems. It's quite general. Okay? And this is another picture of this. You are here now, sitting here comfortable. If somebody tries to move you, you go back to. I try to move your chair now, and you will just stay there. Now, when there's an earthquake, this was your position, and it became like this. So you are not comfortable anymore. Lost equilibrium, and you will fall down somewhere here or here or anywhere. It depends on how the perturbation external affect you, but you will be looking for an equilibrium condition. Yeah. Right. And then something I have to mention is that Hawking radiation came with a problem. The problem of the information. And this is where we start to take serious information. Let's clarify this. The black holes eat things. They cannot emit things. Classic. When we put quantum effects, they can emit particles. But Hawking discovered that the emission of the spectrum is thermal. Thermal spectrum has no information. There is no information. Where is that? Where is the information of the black hole then? What happened? Disappeared? The black holes delete information. What's the problem? Then this is one of the most serious problems in theoretical physics nowadays. There are many proposals, people fighting each other. Some people proposing different ideas. Possibly there are non-thermal modes, which allow you to catch information. Other people may other more exotic ideas. But still interesting to see. But this is an open problem. It's one of the biggest problems in physics. Something I want to mention is that the black hole stores information. Because, of course, if the information disappears, it means the black hole has information. And information is contained in its entropy. The entropy of the black hole in the surface of the black hole. The event horizon contains information of the black hole. And that information I can have access to. So this slide explains what I was talking. What is information of the black hole? The area of the event horizon defines the entropy of the black hole. The entropy of the black hole is proportional to the area. In ordinary thermodynamics, if you studied thermodynamics before, the entropy is proportional to the volume of the objects, not to the area. But in black holes, the entropy is proportional to the area. Many people have done the calculation and it comes out to be like that. So, well, if the information on the if the entropy is proportional to the area, it means all the information on the black hole can be extracted from the two-dimensional surface of the event horizon. Yeah. So, which is the most basic concept of all, which is a more fundamental concept in physics, and people have explored it in different ways. So, the entropy measures the amount of information inside the black hole. So now, for understanding the black holes, technically, since they have information, of course, we should be able to portray them as bits or qubits or so, right? Then we have to understand the difference between bit and qubit. In general, the computers, they store information in zeros and one. I think this is clear. If I have 2 bits, I can have 0, 0, 0, 1, 1, 0, 1, 1, right? 4 options. When I have qubits, 1 qubit alone mixes the 0 and 1. Remember the showing a cat alive or that? The same. It's 0 or 1. So I can define a wave function which is 0 and 1 at the same time. And then when I put another qubit together, I have a richer amount of combinations. Not only 0, 0, 0, 1, but a bunch of combinations depending on the parameters in front of the terms. This is something I will mention later. Let's compare. Classical bit is this 0 and 1. This is a qubit. This is the Bloch pair. I think we have studied quantum mechanics before, and this part. These have been the courses of advanced quantum mechanics. Not in the ordinary quantum mechanics you see in bachelor probably, but you see a course in advanced quantum mechanics. Some professors, they focus on this. And you can see combination of 0 and 1. This is a mix. Perfect mix. This is only 0, this is only 1. And if you put the vector somewhere else, this factor changes. It's not 50-50 anymore. It will be, so this means 50% of chances is 1, 50% of chances is 0. If I here is 100% chance is 0, 100% chance is 1. But if I put the vector somewhere, the percentage is changing. Well, the consensus is that you can mix zeros and 1. This is the concept of qubit. It gives you the capability to store more information than the ordinary bits. Because naturally, if I put this qubit with another qubit which has 0 and 1 with different coefficients, I have to multiply, and I can change all the possible combinations. It gives me a richer structure. Give me a more possibilities, much more possibilities than it is. What's the problem of quantum computers? Quantum computers is a reality. We have laboratories actually in China. They have done 108 qubits already, maybe. Well, the problem is to do it macroscopically. The larger you try, the more qubits you want to keep. There is a higher chance to destroy the quantum effect. Yeah? because of course any external perturbations. Yeah. Which is the same problem which has quantum teleportation and this concept and these things. When you try to transfer information via quantum, using quantum effects, for example, I want to send a photon from here to there, and the photon has, let's say, a spin. I send the photon with some spin to there. But any external perturbations destroy the quantum state of the photon. So this is one of the challenges of quantum technologies, to keep the quantum effects. But it's not that it's not possible, it's an engineering problem. Yeah? This is also the Bloch sphere. This is more general. This is a more general qubit. Alpha and beta, because alpha and beta are the sphere. Then I will put parentheses here. This is one qubit. And then I will put another parenthesis and I will put another qubit. Then I have to multiply 0, 0, 0, 1, 1, 1, and 0. And alpha with the other alpha bar here. So it gives me a huge amount of combinations because alpha and beta can take any value between 0 and 1. So you will have a huge amount of combinations. And if you put n qubits, you will have much more capability of storing information than with simple bits. Both the computers, or the computers, they work with bits, they work only with 0 or 1, not with this combination of 0 and 1. So what we expect, what we theorize is that the black holes also store information in this way. Black holes are the best experiments for quantum gravity. We don't have a theory of quantum gravity, but the black holes are the best machines for doing experiments in quantum gravity. Why? Because gravity is huge near a black hole. And when gravity is huge is where the quantum effects should appear. Hawking radiation is the first quantum effect, but it's semi-classical because we have to work in general relativity and put a quantum field all the time. But we don't have a quantum theory of gravity yet. There's no quantum theory of gravity. There are candidates of quantum theories of gravity. We have a string theory, one of the candidates. They want to not only to quantize gravity, also to unify the interactions. String theory, which was created initially for modeling strong interactions, and it was kicked out from the science, but subsequently it was put back because people realized that the spin 2 fell. I think it was Schwarz, the guy who realized about that. And Schwarz is the main beauty that string theory became so popular. But you think a good way, not in a bad way. But anyway, the point is that we can also, even horizon, can store information in zeros and ones usually. We can model the gravity in terms of information instead of, some people claim that information is more fundamental than gravity. Of course, this will be too much, but I don't know if we should say that. I don't know if it's true or not, but whatever is fundamental is a matter of choice. Yeah. So, and I must remark that besides the fact that we can use zeros and ones or combinations better because we are doing quantum effects in black holes, combinations of zeros and ones in black holes, there are analog models of black holes. Some people don't know. In British Columbia, William Unruh, for example, and others, they have worked with analog models. For example, you put a fluid, and you put the fluid in a supersonic region, supersonic, traveling faster than the sound, and you throw a sound. What is the velocity of the sound in the air? Where's faster the sound, in the air or in the water? Yeah, well, what is faster, in the air or water? In water. Why is faster? Because the molecules are closer to each other. So in solid, it's even faster because they are even closer. So the signal can propagate faster. When I'm talking to you, you are not listening to me. You are listening to the vibration. You are perceiving the vibration of the molecules of air. Here. Of course, it's different to the electromagnetic waves, which don't require medium propagation, etc. But this is an analog model. If I put a supersonic fluid, obviously the sound cannot catch. This region which is moving here, the sound will never catch. It's equivalent to a unit horizon. This is called living horizon behavior. Or if I try to throw the sound to the other side, cannot escape. Cannot escape. Living horizon. It's better in that way. So some people do this in our models, and of course some people try to analyze information from that perspective. Now let's talk about the flow of information in black holes. There are also some models that they use neural networks. I think this is the perceptron model for the black hole doesn't behave like that. It's not perceptron. The black hole behaves more like sigmoid neurons. Because actually the solution, the Hawking radiation looks like a sigmoid solution. If you have seen the logistic function, you're familiar with that sigmoid, your logistic is the same, only that the sigmoid is like the normalized version of the logistic function. Okay? It's the normalized version. But you see the Hawking radiation, the solution of the black body spectrum is exactly a sigmoid or a logistic function. It's the same. So let's say that when we try to model the black hole as neural networks, which is possible actually, we use sigmoid neurons. But when we analyze these cases, when we want to analyze information here in this neuron and how it goes to this neuron, of course we could put zeros and one, but equivalently we can expand a quantum field. This is a quantum field expansion here. Information enter, information output, and this is a loss of information, which is what happened more or less in a black hole. Black hole, when they emit when they emit radiation, technically the information is lost. If it's completely thermal, information is completely lost. If it's partially thermal, it's partially lost. So technically, the black holes disintegrate information, and this can be analyzed via neural networks. This is my times, okay? Let me see. Yeah, okay. So this is a way to perceive how the black holes manage the bits and qubits. Everything is in the surface of the black holes. All the bits or mixes of zeros and one are on the surface of the black hole. And the entropy of the black hole measures this information. Now, let's go to basic thermodynamics. What is the entropy? What does it measure the entropy? Any idea? If I close this room and I put some, I don't know, hydrogen or any gas, neon, or whatever, what will happen? It will expand. It will take the shape of the room. When it expands, what happened? Before the gas was compact, so I knew more or less the location of the molecules, more or less. So the entropy was lower, less disorder. When the gas expanded, this spontaneous process increased the entropy because now it's more difficult for me. Where are the molecules? It's more disorganized system. Exactly. Very right. Exactly. Disorder. When I throw this object to the floor, it has energy, right? Back energy. So what happens when the object hit the floor? The energy disappears? No. Where did it go? It's on the floor. Well, what happened? I can use that energy or not? I cannot use it. Why is wasted? Well, it's a way to say it's wasted. Somehow it's wasted. That's called irreversibility, you know, technically. It's like you cannot take advantage of that because the entropy increases. Now that energy is distributed in a bigger amount of degrees of freedom. It's distributed in millions of molecules. And now it's more difficult to know where is it and I cannot use it. This is entropy, this is increasing entropy. The black holes also have entropy. But the difference is that the black holes have two things. First, the heat capacity is negative. The heat capacity of a black hole is negative. Normally, every object has heat capacity positive. What is the heat capacity of an object? For example, water has good heat capacity. A metal has low heat capacity. What does it measure the heat capacity? The amount of heat I have to input or energy I have to input in an object or a system for increasing 1 degree. So that's why I use the water as a refrigeration in the car. On the car, I put water in it. We call it radiator in Spanish. It's radiator or something like that. It should be in English. Because the water, you can input a huge amount of heat or energy, and it takes a lot of energy to increase 1 degree. It doesn't increase so easily, the temperature of the water. Well, if you put another liquid or you put a metal or whatever, obviously the temperature increases fast. That's heat capacity. Well, the black hole's heat capacity is negative. It means that when the black hole starts to evaporate and start to shrink, its temperature increases, which from the perspective of normal objects doesn't make any sense. Well, in black holes, this is what happened. And this is what made the black hole unstable, highly unstable system. Always trying to look for an equilibrium condition, but never finds it. It's unsuccessfully stable, never stable. So in any case, whatever it is, we can define entropy and heat capacity in the black hole, and the entropy is proportional to the area, and the entropy it is a measurement of the information of the black hole, and information of the black hole can be stored in zeros and one or mixes. If we introduce the quantum effects, mixes of zeros and one. So qubits. Now there are not only zeros and one, and now that people have proposed neutrinos, who doesn't know neutrinos here? Neutrinos come in 3 flavors. Now some people are proposing that instead of using two options, 0 and 1, we could use 3 options with the 3 flavors. That will give you higher possibilities to store information. The difficulty is that the neutrino is difficult to, it almost doesn't interact with anything. It's difficult to manage that part. Anyway, it's just a comment. So now I think I can conclude. So before concluding, well, this is the classical black hole. The black hole evaporates and emits radiation, but that radiation doesn't have information. The result of it gives you thermal spectrum. When something is thermal, there is no information. So there are no zeros and one flying there. So this is the black hole information paradox. Where did that information go? Maybe Harry Potter. No, I mean, we don't know. But there are some papers. Recently, I published one with a collaborator in classical quantum gravity. We propose non-thermal modes black hole, and there are others. Those calculations you saw before, which I didn't want to explain because I didn't want to complicate it, were done by me actually. But those are from another paper. The point is that if an object has information and is evaporating, it's obvious that there should be information flowing away. There must be information. And if not, what happened with that information? This is the black hole information paradox. Discovered by Stephen Hawking himself. He discovered the evaporation of the black hole. But he also discovered the problem of paradox. Of course, there are many things to talk about information, quantum information. I didn't mention the protocols of quantum computer, entanglement. There are many things to talk about. Of course, there is limit of time, and I didn't want to complicate so much. Recently, I gave a course of quantum communication technologies in the University of St. Joseph in Macau, and I explained all these things about entanglement and the protocols about quantum teleportation and so on. Which is not true. If you know about entanglement, let's talk a little bit about entanglement. Entanglement is a quantum effect, very interesting, which people are exploring for communication. Is that a particle is flying there, a particle is flying far away, and they are entangled. So when one particle collapses and you have the result, immediately the other particle collapses. Almost instantaneously. Now we know that it's not instantaneous, that there is a difference of femtoseconds. But even so, even if almost instantaneous, you cannot challenge the relativistic principle, because when you do the protocols of quantum teleportation, which I didn't explain here, there is a moment where one of the observers, one of the participants, Alice or Bob, which is the classical name, they have to send by via classical channels some information to the other partner. So that's why those protocols is not that they give us faster transportation of information. It's not that information will be faster to transport, that's false. It will be safer. Safer because something which I didn't explain, but maybe I should explain, is that there are quantum algorithms. The Shor's algorithm, whoever has studied Shor's algorithm, the Shor's algorithm can decrypt, can violate, can be the perfect hacker of anything. Now we have classical encryption, which secures your information, but the Shor's algorithm enter informed, it will be easy to hack that. The quantum protocols of encryption will be fundamental for securing even more your information. But that part I didn't want to include here because, of course, it will be like deviating too much from the main purpose, which was explaining the black hole, quantum information, and all the information appears in black. And the problem of the black hole information paradox, which is one of the open problems right now. And many people claim that they solve it. I solved the information paradox. Many people will say that, but nobody knows because there is no universal agreement. Now we can conclude this talk because it's more than an hour already. We use black holes for understanding how information can be stored efficiently. Actually, something I didn't mention is that the black holes are the objects which store the information in the most efficient way. The nature is historical lesson, guys. The nature is the best master. Why did we create planes, for example? Now we have planes flying. Well, what did men see before? Birds. They saw the birds. Or can the bird fly? Oh, I can make this, I can make it Bernoulli, make the plane fly. You apply Bernoulli to the wings and you make basic Bernoulli equation of fluids, fluid mechanics. The ships, you saw the docks. Then you can, okay, I will make a ship because the docks can do that. Maybe I can create an object. And even if it's metallic, I can make it float because I can make the shape such that the density of the object is smaller anyway than the water and still can float, right? So we're always learning from the nature. And now we are learning from the black holes because the black holes come from the nature and it has been demonstrated that they store the information in the most efficient way. The best store of information. Fundamental aspects of quantum information are learned via black holes. Of course, the black hole information paradox is important because it teaches us many lessons about quantum information. How it moved, how it changed, what it happened, why it became thermal, what happened there, what did happen for information. Maybe Harry Potter knows, or Merlin. But anyway, qubits are fundamental units of information, not only for the black hole, but also in quantum computers. Quantum computers, there are two qualities of quantum computers. It's much higher capability of storing information. They will store because the qubits allow more possibilities. And the second, they will be much faster, for example, than and it's particular, the advantage is when we are, for example, the Shor's algorithm, we cannot use in classical computer. That's why we are safer. That's why we are safe right now. That's why they cannot hack our accounts. If not, your bank account will be empty tomorrow. Because if somebody could use the Shor's algorithm, they could decipher the keys and all these kind of things, and they could extract your money already from that. But fortunately, there are no quantum computers yet. That's why they cannot use it. So only when you have quantum computers is when you can use these quantum algorithms and these kind of issues, which are really discovered. And of course, I want to stop the talk here, and I hope you enjoy it. There are many things to say, but it's better to stop. And you have questions and you want to discuss. And thank you, sir.
And we have a 10 minutes break, so later we can have more communication. 休息10分钟，然后我们可以等会儿再交流。大家如果没有拿到礼品的话，可以在这边，然后洗手间出去，在外面。
So,
Do you believe in the ADS CFT stereo kind of stuff? That